Hello everyone, my name is Eduardo Tominaga. I'm a doctoral student at the University of Oulu in Finland, and in this video I'm going to present our new paper. The name is Performance Analysis of Centralized and Distributed Massive MIMO for Machine Type Communications. This paper was accepted for presentation in the next UCNC and 6G Summit that will happen in June of 2023, that is next month, in Gothenburg, Sweden. In this paper, we are comparing the performance of different massive MIMO deployment schemes. We have a total number M of antenna elements that can be deployed in an indoor industrial scenario according to one of the following schemes. In the case of centralized massive MIMO, which is illustrated in the figure on the left, we have a single base station in the middle of the coverage area equipped with the M antenna elements. Then, for the case of distributed massive MIMO with grid configuration, which is illustrated in the middle figure, we have many access points. They can be equipped with multiple antenna elements, and the total number of antenna elements is still M, and the access points are uniformly distributed on a grid and attached at the ceiling of the factory hall. Finally, we also have another distributed massive MIMO alternative, which is the linear deployment, illustrated in the figure on the right. And in this case, the access points, they are serially connected around the four walls of the indoor industrial scenario. In this work, we are studying the uplink of a machine-type communications network. Then we consider two different traffic models for MTC. First, we consider regular traffic, where the active machine-type devices, MTDs, they are uniformly distributed in the factory hall. So in this situation, the MTDs, they periodically transmit information to the network in the uplink, and this information is not critical. Then we also consider alarm traffic. In this situation, there is an alarm event in the factory hall, and the MTDs close to the epicenter of this event are activated, and then they send critical information to the network in the uplink. Given the occurrence of an alarm event, the probability of a device being activated is a function of the distance between the device and the epicenter of the event, and also of the intensity of the alarm event. In order to characterize this probability, we utilize something called alarm triggering probability function, ATPF. In this case, we adopt as the ATPF a one-sided scaled Gaussian function. So this function can be observed in the figure in the left. In the y-axis, we have the probability of MTD being activated, and on the x-axis, we have the distance between the device and the epicenter of the event. And then we plot this function for different values of nu, which is a parameter that characterizes the intensity of the event. Then, when we adopt this ATPF, the spatial distribution of the MTDs, that is their position in the spatial domain, follow a 2D Gaussian distribution, and this is illustrated in the figure on the right. We resort to Monte Carlo simulations to numerically evaluate the performance of the different mMIMO deployment schemes under both regular traffic and alarm traffic. In Table 1, we can see the simulation parameters. We evaluate the performance for different total number of antenna elements, M, different number of access points, Q, different number of active MTDs, K, and also for different sizes of the square coverage area. Each access point is equipped with 4 antenna elements. The system operates at a carrier frequency of 3.5 GHz, and we consider that all MTDs transmit in the uplink with the same fixed power. We set a target data rate R equal to 1 bit per second per hertz, and then we evaluate numerically the outage probability of the system. In the case of alarm events, we simulate the occurrence of a single event with a given position and a given intensity. In the figure in the right, we have our first result. So here we are plotting the outage probability as a function of the number of active MTDs given a total number of antenna elements and the size of the square area. And herein we are considering centralized minimum mean square error combining. In this figure, we observe that under regular traffic, the distributed mMIMO schemes perform much better than the centralized mMIMO scheme, but then, interestingly, under the alarm traffic, the centralized mMIMO performs better than the distributed mMIMO schemes. So here we have our next simulation results. So in the figure in the left, we plot the outage probability versus the total number of antenna elements of the system for a given number of active MTDs and a given size of the coverage area. We observe again that under regular traffic, the distributed mMIMO schemes outperform the centralized mMIMO scheme. But then, under alarm traffic, when the number of antenna elements is low, under 32 antennas, the centralized mMIMO presents the best performance. And then, as we increase the total number of antenna elements in the system, the distributed mMIMO schemes become increasingly more advantageous than the centralized mMIMO scheme. Finally, in the figure in the right, we plot the outage probability as a function of the size of the square area, which is here the length of the side of this area. Again, under regular traffic, any of the distributed mMIMO schemes perform better than the centralized mMIMO scheme, but then the centralized mMIMO has a performance in between the case of grid deployment of access points and linear deployment of access points. So we also note in all the numerical results that if we compare only the distributed mMIMO schemes, the grid deployment of access points has always a much better performance than the linear deployment of access points. Thank you very much for watching this video. The preprint of this paper is already available in arXiv, and the simulation codes utilized to generate the results are available in GitHub. You can find both links in the description of this video. Please don't forget to like the video and subscribe to our channel.